So as Brian said, I like to walk the fine line between astronomical instrumentation and then actually doing what a traditional observational astronomer does, which is go to the telescope and use the instrument to study something about it. I study distant galaxies, but I will thread through today's talk a lot about the work I do in instrumentation, in particular in my laboratory at UC San Diego. I think one of the means for coming to a colloquium is really to share kind of who you are and meet with all the great people here at UC Riverside today. I won't cover all of the topics I work on, but just to highlight some of those, I work on adaptive optics instrumentation. I will describe what adaptive optics is. And I work on building cameras and spectrographs that go behind adaptive optics systems on really large telescopes. So I have a project which we'll talk about, which is the 30-meter telescope project IRIS today, which I'll get to. I'll talk about a project to clone IRIS to Keck Observatory, which we called Liger. Liger is a hybrid animal between a tiger and a lion. So that's where it came from, TMT and Keck kind of making a hybrid animal. I did a lot of work on Keck OSIRIS, which is this integral field spectrograph. I will describe what an integral field spectrograph is. And then I'm going to touch on two science topics, high-redshift galaxies, how they rotate, how they move, what's the evolution of them, and then in particular, at the centers of those galaxies, what happens with the supermassive black hole, and how do they co-evolve together is kind of the big picture question. I also work on extreme adaptive optics. I do work with thermally pulsating AGB stars with the Gemini Planet Imager. And then a large, big topic I work on in the lab is SETI, the search for extraterrestrial intelligence. And so I do a lot of instrumentation at optical and infrared, but I will not be talking about that today. But I just posed that to you guys if you're interested in SETI in the future. So I'll start with these two topics. First, talking about Keck Observatory and OSIRIS, and as well of distance. High Z stands for high redshift. Okay, look back times of about 10 gigayears, 11 gigayears ago. So my lab is the UC Optical Infrared Laboratory. We do a lot of instrumentation. My day-to-day life is a lot embedded into the instrumentation. A lot of the science I'll show you today are highlighted from the 3 graduate students that are in my lab. So big picture, history of the universe. This is what galaxy formation and evolution is all about. We're interested in coming from the Big Bang. I don't have a laser pointer, but we'll go from the right here. The Big Bang all the way out into present-day spiral-like galaxies. Okay? How do they evolve? How do we get into a Milky Way of today is what we're trying to answer. On large-scale structure, lambda CDM, so cold dark matter simulations and cosmology, have done a really good job at explaining the large-scale structure of the universe. But where we struggle is understanding the intricate, detailed astrophysics of individual galaxies. So this is NGC 1232. Oh man, I do want to hit the lights because it's so pretty. Can I hit the lights for 1 second? Is that weird? It's just such a pretty image. I'm an excited astronomer, so I have to show you this. But see, it's worth it. Okay, so NGC 1232 is kind of like the Milky Way analog. If you could like fly out of the Milky Way, look back down on it, this is what we would look at. Of course, we're inside the Milky Way. We live in suburbia in these outside disks here. Okay, we have the central bar and bulge. And out in the spiral-like galaxies, you can even see in this 3-color composite that you see star formation happening, the sites where newly formed stars are forming. And there's a lot of astrophysics and physics within how you build up morphologically a galaxy like the Milky Way today. How do you get a supermassive black hole at the center? How do you get a bulge? How do you get a bar? And how do you get it into a disk? Okay? So fundamentally, we're trying to understand how do we make a spiral-like galaxy. If you look around locally, 70% of all of our local galaxies are like the Milky Way. So how does this come into play? So we're interested in, do you want me to turn back on the lights? Okay, this is like just so you guys, I can't see anybody. Oh good, I wanted exercise today. Let's see. Okay, sorry. All right, so we're interested in how do galaxies and supermassive black holes form and evolve, right? That's the big scale picture. But what comes into this play? What do astronomers are talking about? And the idea here is, what is the galactic metabolism over cosmic time, right? It took about 11 billion years to get to a Milky Way today. what was that history? What was the gas accretion to form the Milky Way? What were the outflows that occurred to make that process? How was the star formation? Did it go episodic, or did it come into a burst? Wow, this is, okay. And then what's the history of the interstellar medium? Okay, what's the history of the gas and the dust? And in the models today, what they try to impose are things like stellar feedback, supernova feedback. So you need to inject energy and momentum into the ISM, heat it up to maybe inhibit star formation to occur. And then how do the roles of supermassive black holes? Quasars, really, really luminous AGN. AGN is an active galactic nuclei. It's a supermassive black hole, rapidly accreting material, and it's incredibly luminous. Okay, so we're interested in, this is an M-body simulation that's showing some of the astrophysics here, but we want to go into high redshift to try to see how this evolves over cosmic time. So why high redshift? So first off, the majority of stars, so if you think about stellar mass of a galaxy, and if you think about the mass of the supermassive black hole, the majority of that is formed at redshift 1 or 3. And so that's a look-back time between 7 billion to 11 billion years ago. So if you look at the age of the Milky Way disk, it's roughly about 11 billion years old. Of course, our sun is not that old, right? But this is just showing star formation rate, so how quickly you make stars in a certain volume versus redshift. It peaks here roughly at 10 billion years. And similarly, if you look at the accretion rate, how quickly supermassive black holes are accreting material, it occurs around that same time. Okay? So if you go back and you're able to look at distant galaxies, you're seeing the peak of their formation time. Now, getting to this idea of feedback, which I'll touch upon in today's colloquium, if you look at kind of like the luminosity function, in this case, the y-axis represents the stellar mass of a galaxy per dark matter halo that it's residing in, versus a dark matter halo, you see kind of the peak of where it fits in here. And you see that there is, on the low mass end, a drop. And a lot of models like to think that there's energetics coming from stellar feedback or supernova that's inhibiting that formation. And then on the high luminosity end, they believe active galactic nuclei, the energetics of that accreting material, even though it's really just at a compact center of the galaxy, is influencing the galaxy at tens of thousands of light years away. Okay, that's a challenge if you think about this. All right, so we're interested into high redshift galaxies, distant galaxies, and we're interested in trying to understand the energetics that go into the gas and the dust and the star forming histories of these galaxies. Now, to do this, as Brian implied, is actually really hard. You're looking at galaxies that are about 10 billion light years away. From cosmology, the surface brightness of that galaxy fades as 1 plus z to the 4th power. So they're incredibly faint. But the angular size, so how big a galaxy is at redshift 2, is quite tiny. So this is showing the angular size, okay, versus redshift. If you like time, it's on the top of the x-axis there. On the left part of this axis, that's today. And if you want to study, so I have on the right here a galaxy here. We live about 8 kpc out. If you want to study the substructure of a galaxy, like that bulge or spiral arms or the kinematics of it, you have to get to very good angular resolutions. Okay? So let me demonstrate. An arc second is about the typical size of a redshift 2 galaxy, the whole thing. Okay, so if I want to look at it, it's an arc second in size. If you look at the scene just from atmospheric turbulence, it blurs it, okay, to about an arc second. So if you have a 10 centimeter telescope or a 100 meter telescope, it doesn't matter, right? The atmosphere blurs it if you're at the ground. If you want to study something like the size of a galaxy bulge, so about 500 parsecs in size, you have to do better than the scene profile of the Earth's atmosphere. And the way to do this is you need to get to the diffraction limit, so the lambda over d of your primary aperture. Okay? So Keck, which is a 10-meter telescope owned and operated by University of California, gets the size about at J-band 1.3 microns. You'd be able to study galactic bulges at any cosmic time. Okay? Right? And this turnover if you're wondering, right, has to do with the accelerating universe.
Why the universe size turns over?
The universe is accelerating, right? It actually, yeah. Good question. So we want to get to diffraction limit 8 to 10 meter class telescopes. We need large apertures because they're faint, but we need to get to the diffraction limit of those apertures to get to the angular resolution to actually sample those little tiny galaxies, right? So how do we do that? And I believe a lot of people have heard about adaptive optics. Since it's a theme, a pretty heavy theme in my talk, I just want to make sure we're all on the same page. So adaptive optics corrects for atmospheric turbulence in real time, basically millisecond time scales, as you're seeing turbulent profiles change. And what you do is you generate a guide star. So in green there at the top on the left shows either a natural or a laser guide star. And then you have your distant galaxy in red that you want to target. And you use the guide star to effectively measure the wavefront of you have a plane wavefront. It's pristine and perfect. It's been traveling thousands or hundreds of light years till it hits the Earth's atmosphere. And then you get a potato chip, right, that's just wobbling down as it goes through Earth's atmosphere. What we do is we use a wavefront sensor here that is able to monitor that star, the green star, in real time. We see the corrugations in that wavefront. We have a computer computing that, and then we have a small deformable mirror with pistons that change. Basically, if you have a potato chip, it inverts the potato chip to make a plane wavefront. Okay? And so what you get in real time is then a plane wavefront, and you use at different wavelengths, you're able to take a real picture. And this allows astronomers to use any telescope. Now most 8 and 10 meter class telescopes has an adaptive optics system with it, so it can sample at the diffraction limit. Okay? So you go from, right, a scene. So this is on the top part. That's your 1 arcsecond seeing disk. You would not tell the difference. You turn on the AO system, and you get your pristine point spread function. And then with data, you get a blurred galaxy, and then maybe you're able to see a secondary large Magellanic Cloud to the system. Okay, so this is adaptive optics, and a lot of the instrumentation I do is behind this, and I'll get to why this is important for challenges here. Now, you probably have heard several galaxy formation talks, in your time here at UCR. It really is a lot of trees in the forest, but we're all trying to do the same thing. Astronomers like to classify galaxies based on what wavelength they discover it, what kind of mass it has, okay, are they different colors, are they red, or they're blue, right? It really fundamentally comes down to this. So this is my zoology of distant galaxies. On the left, you have star-forming galaxies, and then you have every single acronym that people come in and talk about. And then on the right, you have passive galaxies, right? Passive red dead galaxies that are over here. And a lot of astronomers go through different classification schemes because there's selection effects of how we do this with our different surveys. And I'm going to do the same. So what we do is we look at optically selected galaxies, meaning that they were discovered in another survey at optical wavelengths. They're at redshift 2, so that light has been redshifted into the near infrared. Okay? This is important because these guys are bright, and I'm going to come back to this as well. So right now, today, we're looking at kind of the brightest, most massive galaxies with adaptive optics. But there's all these other sources that we could be targeting right now. But the majority of the surveys to date do optically selected. And what did they discover? So when we started this project about a decade ago, we went after and looked at these redshift 1 galaxies. We used adaptive optics. We wanted to understand how they rotated, the galaxies internally rotated. We want to understand about their energetics. And actually what we discovered was something that we didn't really predict. Instead of there being really clumpy, irregular forming galaxies at redshift 2, we found that they were all sitting in kind of disk already. So even way back 10, 11 gigabit years ago, the disks were just starting to form in these systems, but they're highly turbulent disks. Okay, so there was a lot of energetics in the disk. And we define this by dispersion dominated. So the velocity rotation divided by the dispersion of it was basically less than 1. For the Milky Way, it's about 15 or 20. Okay? And we also found that the star formation was occurring rapidly in very, very, very compact clumps. Okay, massive clumps. It wasn't just being dispersed through the galaxy. And so we see on the top here some rotation curves. We see in these same similar galaxies, we're seeing resolved clumps here. This bar here represents an arc second. Okay, so we're getting substructure of distant redshift 2 galaxies here. And similarly, at a different redshift, you get large clumps. Now, this is hard work. Using an adaptive optics system is time-consuming and needs special conditions. So really, there was about 100 sources, up to date, maybe 150 now, that have been done with adaptive optics at high redshift with an integral field spectrograph, which I'll get to. So this is at high redshift here, a high redshift sample here. But you notice that there is this desert. So we go to the more local systems, right? This is observed instantaneous star formation rate versus time. And this was the majority of those samples that showed turbulent disks and clumps. And because I'm an instrumentationalist, I was like, I want to do this region. Why can't we do this? And it turns out the limitation had to do with our instrument. So I've been using a lot of words like OSIRIS and names of instruments, but what is this? So OSIRIS is an integral field spectrograph. It uses a lenslet array at the focal plane. So instead of putting your detector on a camera, you have a lenslet array, a little micro lenslet array. So every lenslet's about 150 microns in size, and then you're imaging the night sky to that lenslet array. And then behind the lenslet array, there's a spectrograph where you disperse it. And you get, in the near-infrared range, you get a very small field of view, okay, 5 by 6 arc seconds. We have different spatial sampling for the astronomers. And we designed this instrument and built it to do really everything. I use high redshift galaxies, but it's really some of the most exciting science comes in the solar system, like imaging Titan. It was the first ground-based any observation showing precipitation on another surface, and that was Titan. It was raining methane. So what do we get with an integral field spectrograph? You get X, Y spatially, like you would for a picture in a camera. But at every pixel location, which astronomers call a spaxel, a spatial pixel, for every spaxel, you get a spectrum associated with it. And this is incredibly powerful because it means you can make a narrowband image anywhere in this data cube. So how does this work? So on the left, you see you have re-imaging optics. I said there were different plate scales, so this is just a traditional camera. If you imagine your old ray tracing, you have your collimator, you have a camera, and then here is the focal plane of that lenslet array I was describing. So this is imaging the plane of the sky. The lenslet then focuses it down to a little pupil. So you end up with all these little tiny pupils, okay, thousands of pupils at the back side here. And what you put those little pupils to is you re-image it back into a traditional spectrograph. So you have a collimator, a grating, a camera, and then for every single pupil from every lenslet, you disperse and you get spectra across it. Okay. And a design choice was a design flaw for OSIRIS, but people who were being conservative at the time, is that they used what's a single fixed grating. So this is about 23 centimeters on its side, and it's gold-plated, and it has a very coarse ruling if you're interested in grating optics. So this was a very challenging grating to manufacture. But it's a single fixed grating that has to operate in multiple orders. Okay? And there was a fabrication problem with this. So what we did is we went in. So one of the reasons why we couldn't go to that redshift regime was because of problems at that wavelength range. And so several years ago, I had a student. We worked with R&D of companies, and we fabricated a new grating. We installed it, and we got dramatically better performance at Keck. So this grating is now installed and used at OSIRIS. And we get about a factor of 1.5 and even a factor of 2 in sensitivity gain when we installed this grating several years ago. And this allowed us to then begin to populate this region at redshift 1. So once we had better performance at bluer wavelengths, we used that new grating, and we went after these redshift 1 galaxies. Etsuko Media, a graduate student who's now a support astronomer at Subaru Observatory, did this for her thesis work. She looked at velocity profiles of redshift 1 galaxies. This is showing, so we're going to show several of these plots, so let me walk through this. On the left here is our observed velocity, line of sight velocity. So red means it's redshifted, blue means it's blue shifted. And what you see is a classic spider program, a spider overlay where you see this is basically rotation of a galaxy. In the middle shows our model. So we try to model the kinematics of that galaxy. We subtract it, and we're left with the residual. So light pink green here means 0. So we went through a dozen of these sources, and what we found is that at redshift 1 in these star-forming galaxies, we basically had rotation in place. But probably more interestingly for this survey is that we found that even at lower redshifts as we marched down, we are finding really clumpy systems. So the stars that were being formed were in these really high compact starbursts. And we were able to resolve about 58 of these resolved clumps. And so the sizes of these were about half-light radii of 0.3 to 4.5 kiloparsecs. And for single clumps, we get as low as 1/10 of a solar mass all the way out to about 25 solar masses per year. One of the things we were interested in this was trying to understand if there was astrophysical differences in how star-forming regions at high redshift formed comparatively to the local regime, and get back into these questions about energy feedback. So I had another student, Maren Cousins. She went in and compiled everything. She said, I want to know every integral field spectrograph observation ever that resolved clumps locally to all through high redshift, and collated it to try to explore if there were scaling relationships between the low redshift star-forming regions we see in local galaxies today to that of scaling relationships at high redshift. And this is just an example from Cousins' paper where it shows a local region where star-forming regions were found. We see that we had high star-forming regions, low surface brightness. This is the surface brightness of star formation rate, high redshift lens and unlensed systems. So we wanted to go through and just get everything possible and then explore this. So Maren did this, and she wrote some MCMC code that would specialize in trying to fit these scaling relations. And this shows this whole sample. So for astronomers here, H alpha is the Balmer 3:2 transition. It's an ionizing emission line. It's a really good tracer for star formation. So what I show on the x-axis is the luminosity of H alpha. Okay, so it's gas in the star forming region that's been ionized that's showing. And this is the radius of an individual clump. Okay? And what you see here is you have a local distribution here, okay? It's a large scatter, and then this is where the high redshift system is fall. Okay? Immediately you see orders of magnitude difference in just luminosity here. And that's interesting. We wanted to explore that. There are bias and observational selection effects here, but we were interested in exploring this relation. So one of the first things that we don't have to do to fit anything is that the universe is giving us something where there's a lot of scatter. So on the y-axis, we have the surface density of star formation rate. Okay, this is per clump, so it's not a whole galaxy. It's just a clump within a galaxy. And you have the radius of the clump. And we plot in gray our sensitivity limit. Okay, we can't say anything's real here. But there's also a null region. So there's something saying in astrophysics, we can't make anything bigger than this. Okay? But several orders of decks of scatter here. And one of the things we started looking at, especially, I won't have time to explain this, but it has to do with local scaling relationships between molecular glass and ionizing gas of local regions, was to put a cut. And we explored different cuts. So what we just simply did, very simple, is that we said, let's just look at the galaxies that have high surface density. So they have high concentrated surface density of star formation rate in the yellow. And then let's look at all the stuff that has low surface density star formation rate, and let's see what we get. So is there a break in our system? And by default, we find that what we get from this is that in the high surface density rate, where you have a high surface density of star formation rate, we get scaling relationships that go as L as R squared, okay, the radius squared. In the low surface brightness, right, these are kind of the local distributions here, you get something that scales as the luminosity R cubed. And in the literature, there was a lot of work, people trying to figure out these scaling relations, and a lot of it high redshift was pushing for RF2, but there was kind of this disconnect locally. And there's a couple astrophysical reasons we can try to explain, albeit this was just one or two explanations of why you get this. So I'm going to try three things here. One is just tumoury instability. So you have gravitational instabilities. This is a simulation that you see of a big, large disk. It's 10 kpc. One of the things they like to show is that you get these large clumps, and it's simply related to gravitational instability of the gas collapsing down, and within tumoury instability, you get something like an R-squared profile. That was known. It's not like we've made that. But how do you get R of cube? R of cube has been known as well. It's just what's called the Strömgren sphere. So locally, if you have an ionizing region, right, just to get back to our astrophysics here, you have a star-forming region, you have stars forming, you have ionizing photons coming out, it's ionizing the gas around it, right? And we are seeing the gas around the stars, right? That's where the luminosity is coming from. And you can show these scaling relationships locally. We've known for years that they scale roughly proportionally to the radius cube of that star-forming region. So at high redshift, people were arguing you have R squared. At low redshift, for years, we say, okay, we have R cubed. But our break here is implying something about the surface density of gas. So you can explain both without tumoury instability. So the way to do this is if you have a turbulent disk, okay, and you apply a Strömgren sphere, so you have ionizing photons here. This here is the thickness. So you're looking at a galaxy through the Frisbee disk, right? So we have a Frisbee disk. Here's our disk. We're looking through it. It has some scale height in that disk. And inside that disk, you have clumps of star formation occurring, like these big starbursts. What happens when you get to a point where the starburst and those ionizing photons break out of that size of that disk? So in normal situations and low surface density, like in the Milky Way, that beautiful picture I showed of NGC 1232, you get just these small Strömgren spheres forming in those spiral arms. But at high redshift, if you go and you get to these really large clump size, you're going to get to basically the scale height of the disk, and you're basically going to blow this out. And Marin does a nice job showing this analytically, how you just basically get to an R-squared profile. Okay, so the other topic I want to do, I told you it was going to be a smorgasbord talk, but this is just showing some of the work we do at high redshift. You can't do this without adaptive optics. Even space-based telescopes don't get to the angular resolution, because think of lambda over d. You need that 10 meter in that denominator. Okay, so I want to talk a little bit more about quasar hosts, and then I'm going to go into instrumentation. So I talked about big scale, the disk of the galaxies, how they're forming and evolve. I want to come back to a question about supermassive black holes. So we're interested in understanding the host galaxy. So if you have a supermassive black hole at high redshift, we want to know what kind of galaxy it sits in for a given mass scale. And this is really important, getting to this interest of understanding how supermassive black holes and galaxies co-evolve through cosmic time. So we want to know how, if it does occur, how active galactic nuclei affects the gas of the stars and the stellar mass of the stars. And people have tried this for decades. When I got into this, I was really interested in a techniques paper. I looked at it as a challenge, because I came from an instrument side and an integral field spectrograph side. I actually kind of just wanted to know how good we could do things with an IFS. But it turns out everybody tried to do this. So for years, people tried to take Hubble Space Telescope. You have a quasar here, okay, but you have a point spread function that just comes from your observation, embedded on your fuzzy little diffuse galaxy that you don't know what it looks like. You model a PSF, you subtract it, you're left with this faint residual, and then if you cut this here in this axis, you try to show how the profile of the stars deviate from the point spread function of your source. This is hard, tedious work. And people tried to do this for decades with Hubble Space Telescope. What we were interested in doing was going after quasars, but using adaptive optics and integral field spectroscopy to do that. So we did this with a sample of radio quiet and radio loud. I just want to describe the technique here. So you remember we have a data cube, x, y, lambda, and we look at a quasar. Again, a quasar is incredibly luminous. It's essentially a really, really, really bright star. If you know about exoplanet imaging, and you have a really bright star and you have that really faint exoplanet, when Earth is about 10 to the minus 10 fainter than that star, okay? Jupiter's like 10 to the minus 6. We have a contrast problem too. We have a really bright quasar, but we have this fuzzy little galaxy on top of it, which you don't know anything about the shape of it. A planet is a point source. But that contrast level is about 10 to the minus 5. So we needed to get to about a 10 to the minus 5 contrast, remove the super bright quasar, and get left with your faint underlying galaxy. So how do we do this? So this is just kind of raw data with OSIRIS. This is data numbers per second. You can think of it as flux versus wavelength channel that we're going through. And in blue, it's showing the quasar stellar object, QSO quasar, the broadline region here in blue. Okay? So the broadline region is the accretion disk surrounding the supermassive black hole. It's essentially a point source from our standpoint. This is good news because we don't have to worry about extended emission from the quasar. So what we can do is use these green regions, avoiding sky issues, and make very clean point spread functions that we then model and subtract out the data cube. So I'll show you what that looks like. Okay, this is just what you get. You're at OSIRIS Keck, here's your image. This is, you kind of can begin to see, hey, there's some galaxy here, right? There's the bright quasar, it's a point source on top of it, and you have the faint galaxy. I'm collapsing over the entire data cube. I model my point spread function from the data itself, which is very important because your AO system's changing. You subtract it out, and what you get left is just the galaxy. To very, very good inner working angles, far better than HST. So we used this method and then started building up a sample of these. So Andre Vayner, a graduate student who's finishing up this year, started a sample called QUART. He looked at about 11 radio loud quasars. This means that they have loud radio emissions where there's jets. Redshift range similar to 2. And we're looking at these ionizing emission lines. Okay, so here's our Balmer 3 to 2. Okay, and then we have forbidden transitions like N2, S2, O3. And we chose their data sets to have HST, very large array radio, and then ALMA is a sub-millimeter telescope. This is awesome. I mean, I'm like blown away still by this. This is a 3-color composite, so at different emission lines. Red is H alpha, so you immediately see where the stars are forming. Green is O3. It's predominantly, there could be some emission from the star forming, but you're actually seeing most of this ionization coming from the quasar itself. Okay? And then blue is N2 emission. So we can do a 3-color composite of these systems. So here's his sample now. He's writing up a survey paper for his thesis. You see here's like oxygen 3 collapsed. Here is that line of sight velocity and radial velocity. And here's your dispersion map, okay, the width of those lines, which is telling you the energetics per pixel. So as an example, I just want to go through one source here. This source is called 3C298. It's at redshift 1.5. Here is that 3-color composite. So this is on a side about 30 kiloparsecs. Okay, so if this was the Milky Way, we're at the center, we would be here, but we're way out. Okay, you see your radial velocity here, but what's interesting, you see these massive outflows that are occurring right where our quasar was. And if you overlay that, that's occurring close to where our jets are occurring at the radial lobe. And then you're seeing very, very large velocity dispersions. This goes up to about thousands of kilometers per second, extended out to about 10 kpec. Okay. And so we see these really large booming outflows that are occurring that are basically impacting the entire galaxy. Okay. Similarly, we've done ALMA, which is sub-millimeter. So this is a 3 to 2 transition in CO. And this is an overlay. What we see is a molecular outflow. At the same site as our ionizing region, we get large molecular outflows as well. We do multiple transitions of these lines, and we get about 900 kilometers per second, which means that the galaxy, the energetics from the AGN, is basically taking the gas and just throwing it out of its galaxy, right? At 23 solar masses per year, it's grabbing that material and just ejecting it, which obviously has an impact on how the galaxy grows. One of the main things we're interested in is how does that affect the local scaling relationship. So locally, if you take the mass of a supermassive black hole here and you relate it to the velocity dispersion or the mass of the bulge, it's correlated. So these lines represent what we see locally. It's a correlation. What we find is that our systems here are offset by a couple orders of magnitude. And this is just one system. But we see, based on, this is from CO and our H alpha measurements, we can place that the mass of the black hole is about 10 billion, okay, roughly, and we sit off M sigma. And this is seen by other surveys, okay? So this is only in the last couple of years this is starting to be seen. So again, blue and green represents the local distribution. What I'm showing in light green are what's happening at redshift 6 from ALMA. We're seeing a systematic shift from CO from the M sigma relationship. If we look at our sample and we overplot, we're about a magnitude away. Okay. And other samples are coming online where we actually think this is a real kind of turnover that we're seeing at high redshift. At the very high mass n, I should be very careful to say this, we're at 10 to the 9 or above. Okay. Locally, that's been kind of seen already. This green here is already showing kind of a turnover when you look at the brightest cluster galaxies. So what does this mean? We have a lot of energetics that are going into the system. So I just want to say something about feedback, especially for the Astro grad students. Everywhere you go, you hear talks and people say feedback. It's like this word, feedback. What does feedback mean? Like, what is the astrophysics in that word? Well, there's a lot. That's the problem. People sweep a lot under the rug. I think there's a confusion in the literature, and I wanted to kind of just highlight that today. So there's ejective feedback. So that's when you have these high outflows and you just throw material out. Okay, that obviously impacts your star formation rate because the material is not there to form. Okay, and that comes into outflows. But there's also negative feedback here. So negative feedback is where you actually inject energy and momentum into the interstellar medium because you're heating the gas and dust so it can't gravitationally collapse, okay, or it delays that time. Okay? So this is the negative feedback where you're just putting energetics into the system. Okay? And I just wanted to highlight those two differences because we hear a lot of talks about outflow and feedback, but we also have to think about how this applies to the energy. If you look at this, it's a semi-complicated plot. It shows kind of the energy. If we look at the energy rate of outflow versus the energy of star formation rate versus whether it's momentum-driven driven things within the momentum of the outflow for the star formation rate, you can say whether the outflows are dominated by star formation or AGN. We have one system where we think we may have a star formation-driven outflow, but the majority are AGN. One last thing on this topic, this goes to the future of this, is we are, for the survey, we've collected now ALMA data and KCWI data. So here's the ionizing gas that I've been showing here in OSIRIS. Here's some of their molecular gas that we're getting. And now looking at very, very large scales, like 83 kiloparsecs, kind of asking this question, once you eject it, or what other materials out there to accrete later? How do you build up the galaxy? So we're trying to do this at all size scales. And so this is data to come that we're working on now. Pretty data. The KCWI is great. I know a lot of people here are using KCWI. Okay, so I want to move now and talk about TMT. All right, I love showing this slide. It never gets old. What we're trying to do is absolutely insane. Okay, and we're taking a huge engineering leap in astronomy right now. So this is the aperture size of the Keck telescope. 36 segments phased into a parabola, 10-meter telescope. That's 492 segments phased into a 30-meter diameter telescope. So the diffraction limit here is about 25 milliarcseconds, and the diffraction limit here is about 8 milliarcseconds. And the challenge for our instruments today is this. That is hard to do, to put behind an AO system. And the AO systems are complex. So what is the 30-meter telescope? So it's a 30-meter diameter primary aperture, 492 close-packed segments. We're trying to deliver an adaptive optics system at first light. You don't really make these big beasts of telescopes on the ground without trying to get to the diffraction limit. It's not all about faint stuff. So you want to get to these low resolutions. You get a 20 arc-minute field of view in diameter. The Nasmyth deck, so right here where you put instruments on the right side, that's the size of tennis courts. you have these huge tennis courts that sit on the deck that rotate where you put it. The telescope's in the final design stage, and we're in the production stage for all major subsystems. And if you follow the politics for TMT, we had a positive ruling in November of this last year to allow the permit of construction. And if you have questions, I'll take those questions afterwards. So the readiness of most systems are there. The start of construction's now, like any day. Literally, you probably will be hearing something in the news in the summer. And first light is 2028. Okay? There's 2 sites you may have heard about. One is La Palma as a backup site in the Canary Islands. And the other one's here on Mauna Kea Observatories on the Big Island of Hawaii. Here's the site. Obviously, it's not built yet, but it's right here. Just so for those, TMT is going to be owned and operated by University of California, Caltech, India, China, okay, Japan.
Wait, Canada?
Canada, sorry, thank you. I was like, you could tell I was pausing. I'm like, thank you.
Where were you before San Diego?
Canada, I'm sorry. All right, so you see the light path here, right? So the light, just so we get this is such a nice light path. So, right, the light comes down. Whoa, okay. Light path comes in. Now it's not going to start. Okay. The light comes in, hits the primary mirror, goes to a secondary. It hits a tertiary mirror. The tertiary mirror sends it to this tennis court with your instruments. You can rotate a tertiary mirror that could then send the light to any one of those ports. So you can put multiple instruments on the telescope there. Okay. And it's going to end up on one of the ports for which I work heavily on. So here, the next one here, this is the adaptive optics system right here. Okay. And our port for our instrument sits underneath it, which I'll be talking about. And both this system here and the attachments are only going to be delivered at first light. All other components are second light deliverables. So how do we do this? So I showed in my cartoon just one laser guide star, right? But it turns out if you just, the way I like to think about it is that you have a big dish. A 30-meter diameter is like a Major League Baseball diamond. And that's looking up at the plane of the atmosphere. So if you think between first base and third base, if you look straight up, you're looking through a different column of the atmosphere. And it's actually at that distances, it's quite large. And you need to measure that wavefront error across the pupil of a 30-meter diameter. So what you do is you do multiple lasers. So you have a constellation of 6 lasers. And you do what's called multi-conjugate adaptive optics. And if you're familiar with objects, you conjugate. The deformable mirror is conjugate to a level in the atmosphere for which you're correcting for. And so we have multiple conjugates in that atmosphere. So if you think of the onion layer of the Earth's atmosphere, we're fixing different levels that dominate our turbulent profile. Okay, so it's cooled down. This is the size of a semi-truck that's cooled down to minus 30 Celsius. And this is where we sit, okay, underneath it. By we, I mean the instrument IRIS, for which I work on. So I'm the project scientist of this instrument. We spend a lot of time thinking about science cases, and then obviously I work heavily on the technical side as well. The PI is James Larkin, and this is a collaboration. I mean, this is mega teamwork and engineering work between Canada and Japan and UC and Caltech. So it's a $40 million instrument. We try to go down to blue regions, about 0.84 to 2.4 microns. Incredibly low wavefront error. Okay, we have to get that very, very pristine point spread function of 40 nanometers. We actually do some of our natural guide stars. So we are an AO system in ourself. First order correction. So if you think about a multiple order correction for the atmosphere and how you make your potato chip, right, there's focus of your potato chip, and then there's tilt, and we need to take care of that. We have a wide field imager, and we have an integral field spectrograph. So this is best seen on the plane of the sky. So here's the imager, 4 imagers here. That makes up 34 arcsecond fields of view. There are little robotic arms that sit above this plane that pick off natural guide stars. And then on axis, we have an integral field spectrograph similar to OSIRIS. So if you go here, you have your imaging cameras and then your spectrographs at the center. For this. So why do you want to build this? A lot of reasons. So we have a very large international science team. Our science cases push a lot of requirements. We're trying to get to solar system objects. Like, I love this, except for I don't love one thing we did. This is what we get now. Okay, this is Io. It's the most volcanically active surface in our solar system. It's always the fun thing to say. But in this picture, there's no volcanoes going off, which is the less fun part about it. But if you simulate this, this is the simulation that you would get with IRIS. You'd be able to basically do individual resolutions of volcanoes on Io. Here is an exoplanet case where we will essentially look at the orbits of it. And I bet you guys have been mesmerized by that one, right? This is the galactic center, okay? And what you're seeing is current Keck, okay? That red star is SO2. It orbits the supermassive black hole at the center of the Milky Way every 15 years. But if you get Keck AO, you'll be able to get to exquisite precision where you basically measure 1 year orbits, which will probe GR as well as dark matter distributions at the center. Okay. Amazingly, I love this little fact, you'll be able to study brown dwarfs at the center of the galactic center. Yeah. All right, lastly, I love to pop a couple of ones. Pluto and Charon, here they are. You may have seen one of those beautiful images from New Horizon. Yes, we're not a space-based thing flying out to it, but in a single shot, we'll be able to look, if you look at our integral field spectrograph and overlay it, we could basically get spectra across the surface. And this is interesting because one of the things we learned about New Horizons is that Pluto has an active surface. Okay, it's seasonal. And so there's some very interesting things about why do Kuiper belt objects have more geological activity than we expected. Lastly, I just want to highlight again back this because I love galaxies. I showed you guys this at the start. That's angular size again in redshift. And purple is the size of a molecular cloud. With the TMT diffraction limit, or the giant molecular clouds, you'll be able to study at any cosmic distance. So you'll be studying H2 regions at redshift 5. It also means because you're really faint, in 20 minutes of 30-meter telescope time, you reach the Hubble Deep Field. So as you're doing your spectroscopy of your favorite sources, one of the things we're writing into the program is that you're always taking imaging data because you're getting an HDF for free. So where are we now? We're here. We're in the final design phase. Really, we're kind of inching along with when the telescope will be built. But in truth, the minute we go, we have to build this thing in about 6 years because we have to be married to that AO system in Canada for about 2.5 years because we commission each other before we're shipped. To highlight, we have an exposure time calculator. If you're interested, you can go to the TMT website. This is a full simulator that you can look at and see what you could possibly do with IRIS. I love to hear new science cases. In my last minute here, I'm going to just highlight that one of the ideas that we want to do, and we've known about it for years, is that you could take IRIS, and it turns out the plate scale from the 30-meter telescope AO system is basically the same as the Keck AO system. So you can take IRIS and just clone it and put it on Keck. We have money for the next 2 years to do this, and so the idea is to make Liger, which is essentially this new integral field spectrograph. It will operate at higher resolving powers, and it'll get much larger fields of view than OSIRIS. And just to highlight the fields of view here, this is like the AO system in OSIRIS today. There's going to be a new AO system called Kappa that we're interested in. This is OSIRIS, and this would be the galactic center image I just showed. And so we're working now to put this, we're trying to work to get funding to start at the beginning of 2021 for Liger. And so part of this has to do with risk mitigation and working as a prototype for IRIS. So I'll stop there. I want to be cognizant of time here, so thank you.
Okay, thank you, Shelley. Questions?
So you mentioned the Hubble Deep Field. Is there plans in the TMT consortium to do something like that? Or they're just going to go really deep and produce a...
So I'll repeat the question. It was, is there plans for TMT to do something like the Hubble Deep Field? No, not yet, but there is a thing where people look at legacy programs where people will pull resources and do that. So there's a potential for that. For those that don't know, the first Hubble Deep Field was really just Hubble Space Telescope staring at a tiny patch of the sky, hold up a pen there, the tip of your pen, and they integrated for about 50 days. And so that's what makes it, that's what's remarkable about it. Of course, HST is a 2.5-meter telescope, and that's the difference here. Yeah.
Could you comment on the Hawaii week?
Hawaii Supreme Court, what's happening? Yeah. So if you don't know, if you haven't followed the story, the 30-meter telescope project was geared to put it on Mauna Kea, and there was a contested case from the native Hawaiians about the sacred land and the use of that land and even permitting of that land. They were granted a permit, they were awarded a permit, and then it turns out the state of Hawaii had I agree with it, not a very good process for doing appeal cases. And so one of the things that went to the state Supreme Court was the process valid for the 30-meter telescope to get a permit. And they turned out that process wasn't valid, so then they went back and went through the new process. So we actually changed the way that building permits or industry permits got made in Hawaii for the better. And then they went through the process and they got a permit. And then there was another appeal to the state Supreme Court on whether astronomers even had the right to build on Mauna Kea. And that was the ruling that occurred in November of 2018 that said yes. And similarly in Haleakala and Maui, the Air Force has telescopes, they went through the same ruling. So since November, the 30-meter telescope project has had the right to build on the mountain. They haven't yet. My understanding is they're just working with local governance to try to, how to make this a good, peaceful experience when they do build. And so as far as I know, many of the people at TMT have just been in Hawaii essentially the last 6 months working with local governance on this topic. I don't know if that was the answer to the, yeah.
That's a whole other colloquium.
Yeah, that is a whole nother colloquium. But a really good colloquium. Like, I think we should think about the world for which we do astronomy and physics in general.
Other questions? Okay, I have one. All right, so you were talking about, you have to go way back if you want to show it. Maybe you don't have to show it. The luminosity versus radius of the alpha regions versus, r squared versus r cubed.
Yeah.
And the explanation being that the ionized regions are breaking out of the scale height greater than the scale height of the disk.
Yeah.
But we have a lot of I have a lot of observations of trying to find ionizing photons escaping from those same disks, and we can't find them.
Okay.
It's not typical, and so I'm not sure what's happening there, but it's sort of in contrast with that work, and I don't know if you have comments on that. If it's like the circumgalactic medium that is still absorbing a lot of the ionizing photons.
I don't, and it's a good point for looking at sensitivity limits. I mean, I should have been more careful to say that we're not saying that tumor instability isn't a possibility. We were just exploring in this paper other possibilities to retrain the Strömgren, but you have a very, very good suggestion, and we have not looked at it. So, yeah, it's a good point.
One more question. So you mentioned about the high-redshift, the disk formation process. It's my first time actually to hear this. How big is a sample, observers have that to look at the different stages of the evolution of the stellar disk?
For integral field spectroscopy, like when I get to substructure, it's very little. I mean, we're talking hundreds of sources. But when we look at a single slit, which is the traditional spectrograph, we have thousands of sources. And so those have much larger sample profiles for it. It gets very, very hard at higher and higher redshifts, as you might imagine. Yeah.